In this video, we're going to continue our conversation about the law of sines. In our last video, we looked at law of sines when we were given triangles with angle, angle, side, or angle, side, angle information provided. Pretty straightforward. We have that law of sines proportion that we can use to find missing sides and missing angles. In this video, we're going to look at still using law of sines, but when we're given a triangle in the form of side, side, angle. We like to make sure we do that order, side, side, angle. This is called the ambiguous case. And that's because having the angle and then the next two sides could result in a couple of different cases. If the side opposite the known angle happens to be less than the height of the triangle, then we do not have any triangle. Think about just having a pendulum swinging from that top vertex. If the side opposite our known angle is equal to the height of that triangle, then we have a right triangle. If the side opposite the known angle happens to be greater than the other known side, which is adjacent to the angle, then we have one triangle. And if you're following along in the video, I just described that first, second, and fourth case. And then the last case that we're going to talk about is where we have two triangles. And that's if we know that the side opposite the known angle is greater than the height of the triangle, but it's also less than that other side that we're given. In which case, we can kind of swing that side back and forth, creating two different length bases, and therefore two different triangles. So we're going to practice using law of sines for this, this scenario where we're given side, side, angle. Solve the triangle ABC if angle C is 41 degrees, 20 minutes, side B is 25.9 meters, and C is 38.4 meters. For this particular type of exercise, drawing the triangle is definitely the hardest part. The way I do that is I start by making the angle that we're given first, and trying to make a horizontal line with then measuring up to make that angle. So let's go ahead and start working through setting this up before we can even start working. We're given angle C is 41 degrees, 20 minutes. So let's go ahead and convert that to decimal degrees. So that's going to be 41 plus 20 over 60, or 41.33 degrees. So now that I have that angle in degree measure or decimal degree, I'm going to try to sketch that angle. So I'm going to start with my horizontal line and then sketch an angle of about 41 degrees approximately. And I'm going to label that C because that's what I'm given. And then we're given B, which is going to be that top side. We're going to call that 25.9 meters. And then the next side is going to come off of that side we just drew, and that's going to be side C of 38.4 meters. So I'm not going to quite connect that because I don't really know how that side is going to land. So what we're going to do is start comparing C to the other information that we're given, starting with the side length B that we're given, that adjacent side. Since the side length C, which is opposite our given angle, is greater than side B, then this falls into, in our pictures, that fourth case where we end up with one triangle. So then I can go ahead and continue this leg for side C to finish that triangle, just to give myself that visual. And now that we know that we have one triangle, we're going to move forward with law of sines. So we know that sine of 41.33 degrees over 38.4 meters is equal to sine of angle B, over side length B, which is the 25.9 meters. So I'm going to start labeling the rest of this triangle, the vertices. Cross multiply, we get that sine of angle B is 25.9 times sine of 41.33 degrees divided by 38.4. And then to find the measure of angle B, we'll use inverse sine. So we can find that the measure of angle B is 26.45 degrees. And we can go ahead and solve for angle A since we have the other two angles. Measure of angle A is going to be 180 minus the sum of our other two angles. So minus the sum of 41.33 plus 26.43. We find that angle A is 112.22 degrees. So we have angle B, angle A, and now to solve for side length A, we're going to go back to using law of sines. Sine of 41.33 divided by 38.4 is equal to sine of our angle A, which we just found to be 112.22 degrees divided by side length A, which is what we're trying to solve for. Again, we're going to cross multiply. We get that A is equal to 38.4 times sine of 112.22 degrees divided by sine of 41.33 degrees. We find that side length A is 53.83 meters. Solve triangle ABC if angle B is 74.3 degrees, side length A is 859 feet, and side length B is 783 feet. So I'm going to start by trying to sketch just that angle B. Beginning with a horizontal line just makes it a little bit easier for me to estimate the size of that angle. And then 74 degrees, pretty big angle. And that's angle B. That angle or that side that we're kind of calling our terminal side on B, so that top side, that's going to be side A. So that's going to be 859 feet. And then coming down across from angle B is side length B of 783 feet. And again, I'm not extending that all the way down because I need to see what case we land in. We don't have the side opposite our known angle, so we don't have that side B is greater than side A. So that does eliminate that fourth case. And the remaining cases, those first three cases require that we compare that opposite side, in this case B, to the height of our triangle. So I'm going to draw a perpendicular line to the base of my triangle, which is going to be the height of my triangle. And I can use the definition of sine to solve for h. Sine of our angle 74.3 degrees is equal to the opposite leg over the hypotenuse. The opposite leg now is h over 859. We're going to multiply both sides by 859. H is equal to 859 times sine of 74.3 degrees. And if we evaluate that, we get H is equal to 826.95 feet. And since that opposite leg B is less than my height, that means it's kind of just swinging like a pendulum. It's never actually gonna reach the base of this triangle to complete the triangle. So there is no triangle. Solve triangle ABC. Given that angle A is 29.7 degrees, side B is 41.5 inches, and side A is 27.2 inches. So starting with my angle, 29.7 degrees. And that's angle A. The side above this angle A or adjacent to it is going to be B, which is 41.5. And then we know that A is 27.2. Again, since side A, the side opposite our known angle, is less than side B, we need to calculate the height to determine what case this falls into. So we're going to do that the same way we did before. We're going to find that sine of 29.7 degrees is equal to the height over 41.5. This is opposite over hypotenuse. And that the height is 41.5 times sine of 29.7 degrees. And our height is 20.56. And this is inches. Now, since that side A, that side opposite our known angle, is greater than the height, but less than that other side B, that tells me that there are two triangles. So I'm going to illustrate this. I'm going to extend side A all the way down. But then I could also kind of pivot this same length on the inside. So to the left of my height, making an obtuse triangle. So we're going to highlight our two triangles. The first is that obtuse triangle. And I've highlighted that in green. And then our second is just an acute triangle. I'm highlighting that in blue. We're actually going to redraw both of these triangles to help us see this picture a little bit better, but we will have to go back to this figure, this original figure. Again, that side of 27.2, that's also that same side length, because we're looking at the same side length that's just basically pivoting on either side of that height to make two possible triangles. We're going to start with that acute triangle first. So triangle one was the one that we had in blue. So we had angle A was 29.7 degrees. Side length B was 41.5 inches. We know that side A is 27.2 inches. To start by solving this one, we're going to use the law of sines. So again, we want to make sure we always start with that acute triangle first, and then work on the obtuse triangle, because the obtuse triangle, we're going to have to use some different techniques. So continuing to solve triangle one, we're going to find angle B first, just because we have that side opposite B as well. So we're going to set up sine of 29.7 degrees over 27.2 is equal to sine of angle B over 41.5. And we're going to call this B1. Since this is a new value for triangle one, we're going to have another value for B in our second triangle. So sine of B1 is equal to 41.5 times sine of 29.7 degrees over 27.2. So that angle B1 is inverse sine of that ratio. And we get that angle B1 is 49.11 degrees. Now, real quick, if you start setting up, let's say that green triangle, that obtuse triangle first, and you use law of sines, what you're going to end up having what's going to happen is you're going to get that B is 49.11, and that again has to do with inverse sine. We talked about the parameters that inverse sine kind of operates in, and the outputs that we're going to get when we use inverse sine on our calculator. We're going to get a value from negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. If we look at this green triangle, that obtuse triangle, angle B is clearly obtuse. So if you're setting this up and you get 49.11 degrees, just understand that you're actually solving that acute triangle first, and maybe just pivot and change your picture, because inverse sine is never going to give us an obtuse angle measure. It's always going to give us that acute angle measure. So now we have angle B1, which was 49.11 degrees. So we can now find angle C1 using the interior angles of a triangle. So 180 minus the sum of 29.7 plus 49.11. So angle C1 is equal to 101.19 degrees. And now we can use law of sines to find side C1. So again, sorry for the, common language, but angle C1 versus side C1. We're capitalizing that angle using a lowercase for that side length. I'm going to set this up over here. So sine of 29.7 degrees over 27.2 is equal to sine of 101.19 degrees over side length C1. Cross multiply, side length C1 is equal to 27.2 times sine of 101.19 degrees divided by sine of 29.7 degrees. And that gives us a side length for C1 of 53.85 inches. So that's our first triangle. Now we need to solve our second triangle. I'm going to try to start this up here just so that we can see our other work. So triangle 2 is that obtuse triangle. Angle A we're given is still 29.7 degrees. Side length B is 41.5, so that's still given. And side length A is still 27.2. So what we're going to be looking for is angle B2, angle C2, and side C2. Now to start, to find angle B2, we're going to go back to that original picture we had with both triangles on the same picture. And what I want you to observe is that there's a third triangle created, that triangle that's built centered around the height. And that's an isosceles triangle. We see that that side of 27.2 is on both sides, which means that your interior angles, the lower interior angles are equal. We also see that that lower right angle is B1, angle B1 that we solved for in that first triangle. So we know that this is 49.11 degrees, which means that this is 49.11 degrees. Because the angles at the base of an isosceles triangle are equal, as well as the side lengths being equal. And now we can see that angle B2 is supplementary to this. They make a straight angle. So angle B2 is going to be 180 minus that 49.11, or 130.89 degrees. Now we can also find angle C2. 180 minus the sum of 29.7. 180 minus 29.7 plus 130.89. We find that angle C2 is 19.4 degrees. And then we're going to use law of sines to find that last side length C2. So starting with sine of 29.7 degrees over 27.2, this is going to be equal to sine of 19.4 degrees divided by side length C2. Using cross multiplication, we find that C2 is equal to 27.2 times sine of 19.4 degrees divided by sine of 29.7 degrees. And we get that C2, side length C2 is 18.24 inches. And that's our example when we have two triangles. A 95-foot flagpole is on top of a building. How tall is the building if the angle of elevation from the ground to the top of the flagpole is 35 degrees, and the angle of elevation from the ground to the bottom of the flagpole is 26 degrees? So again, we want to start by trying to set up a picture. So I'm going to draw my building and the ground. And then I'm going to draw my flagpole on top of the building. It's a pretty good flag. My flagpole we know is 95 feet. We do not know the height of the building, so that's what we're actually going to solve for, so I'm going to call that H. But we're given that the angle of elevation to the top of the flagpole, so if I extend out along the ground and I make an angle from the ground to the top of that flagpole from a point, that angle of elevation is 35 degrees. Now, if I form another angle of elevation from that same point on the ground to the bottom of the flagpole, that angle of elevation is 26 degrees. What that tells me is that the angle between those two lines that are marking the angle of elevation from the bottom of the flagpole and the angle of elevation to the top of the flagpole, that's 9 degrees. Now, a building is going to be perpendicular to the ground, so we do have some additional information for these angles. If I think about that angle that's formed, or that triangle that's formed using just the building and that angle of elevation from that point on the ground to the bottom of the flagpole, that's a right triangle. And so we know that if that bottom angle is 26 degrees, that top angle is going to be 90 minus 26, because that third angle is 90 degrees. So the other two angles from an interior angles of a right triangle sum to 90. So this top angle is going to be 64 degrees. Now, if I look at that right triangle that we just were working with, just using the side, the height of the building as the side, so kind of removing that from our picture, we have a bunch of angles. So we've got our lower angles 26 degrees, that top angle 64 degrees. We know this is a right angle, but we don't have any side lengths. Without any side lengths, I don't have a whole lot that I can do as far as using any of our trig functions or using law of sines. So now let's think about the other triangle that's formed. The triangle that's formed with the flagpole and those two lines that we drew to make those angles of elevation. So it's that obtuse triangle kind of sitting on top. Now we know the height of the flagpole is 95 feet, and we know the angle measure between those two angles of elevation sides was 9 degrees. And if we look back at that original picture, we can actually find that obtuse angle as well, because that 64 degrees that we used as the top angle in that right triangle is going to be supplementary to that obtuse angle. So if we're looking at those two angles, they are supplementary. So this obtuse angle in this triangle is going to be 180 minus 64, or 116 degrees. Now that we have angle, angle, side, we can actually find that third angle, but we don't necessarily need to, because if we think about trying to get back to that right triangle that is involving H, what we're looking for, all we need is this bottom leg. So we need to find X, which is that side length between that 116 degrees and 9 degrees. So actually looking at this, I do need to find that third angle, because the third angle is opposite this. So using the fact that all angles inside of a triangle add up to 180, that third angle is going to be 180 minus the sum of 116 and 9. So that's going to be 55 degrees. So now I can use law of sines to set up to solve for x in this triangle. So sine of 9 degrees over 95 is equal to sine of 55 degrees, and I labeled that side length x. So I can use cross multiplication and find that x is equal to 95 times sine of 55 degrees divided by sine of 9 degrees. And we get that x is equal to 497.5. And this is in feet. So now that we have x in this obtuse triangle, we also have the hypotenuse of our right triangle. And now to find the height, we don't even need to use law of sines. We can use just definition of one of our trig functions. I'm going to use sine of 26 degrees is equal to the opposite leg, in this case is the height of the building, over the hypotenuse, which is 497.5. So then our height is equal to 497.5 times sine of 26 degrees. And we find that the height of the building is 218.1 feet.